All right. Now we're come to our next set of characteristic reactions called oxidation reduction. We've talked about acids, we've talked about precipitation reactions. Now we need to get into a whole new game. Turns out that most chemical reactions are oxidation reduction reactions. Okay, we have been looking at them and you haven't known it, but let's define those. First thing we need to do is tell you what oxidation is, what reduction is. Okay. Oxidation occurs when a substance loses electrons. Okay, so in this picture down here, we show calcium metal plus oxygen gas, right, two elements. And what's going to happen is that calcium is going to give up its electrons, right? Metals like to lose electrons. Non-metals like to gain them. Remember, that was an overriding characteristic of metals and non-metals. All right. So that's oxidation. What's reduction? Reduction is the gaining of electrons, so that oxygen is actually being reduced. Now, what is this about reduction gaining? I'll give you some mnemonic devices to help you remember this, but here's why we call reduction gaining electrons. Think about the charge in an electron. Electron has a -1 charge. So a neutral atom, let's just say oxygen, it has a no charge. When it gains an electron, it now is going to have a negative charge. So think about the number line. And we got plus 1, plus 2, -1, -2. Anytime you gain an electron, you're moving right to left on the number line, right? So reduction could be +4 to +2, or -1 to -3. And it's simply because we're acquiring those negative charges in the form of electrons. All right. Here are the two ways to remember this. Leo Gurr, this has been around for ages. Leo Gurr, losing electrons is oxidation, gaining electrons, Gurr, is reduction. Here's another one. Oil rig, oxidation involves loss of electrons, reduction involves gain of electrons. So keep these in mind. All right. Another thing that's very, very important, you can't have oxidation occurring without reduction, or vice versa. When you've got a reaction going on, something is going to be giving up electrons, something is going to be gaining electrons, and we're going to teach you how to decide what's going on. All right. Let me give you an example of a very simple oxidation reduction reaction. The reaction of sodium metal, let's put solid here, with chlorine gas, both neutral metals. Okay, what happens? Oxidation. Sodium, a metal, gives up, loses its electrons. So we write a half reaction. Okay? Sodium going to the cation plus electrons. What is our reduction? The chlorine gas grabbing electrons, creating chloride ions. So notice what we've created: the sodium cation and the chloride anion, and hence, remember, those don't exist. If they're in water, they're floating around, but as a solid, they exist as this big lattice, okay, where all the plus and minus spheres are stuck together in a very defined way. All right. All free elements are neutral. What do I mean by neutral? Meaning no charge, right? If they've got that even number of protons, number of protons equal to electrons, so that is a net neutral, zero charge, okay? So let's talk about how do you determine what's being oxidized and what's being reduced. We need to teach you about oxidation numbers, also sometimes called oxidation states. Okay, and this is simply the plus or minus charge on a particular atom, specific atom. To assign oxidation numbers, we're going to give you a set of rules. Okay, these rules are in your book. I've put down the numbers here for all the 13th edition, the 12th edition, and even the 11th edition. I'm going to go through each of these very quickly, but as usual for this class, you really need to practice this. You need to be able to get very fast at looking at complete reaction, assigning the oxidation numbers to each element in the reaction on both the reactant side and the product side. All right. Rule number 1, I already mentioned this. Free elements have an oxidation state, an oxidation number of 0. Okay, so here's some examples: sodium, beryllium, potassium, lead, hydrogen. Remember the diatomic elements: hydrogen, oxygen, all the halogens. Okay, Even if you got two atoms stuck together, it's got an oxidation number of 0. And why is that? Because you've got an equal number of protons to the number of electrons. Okay. Rule 2. In monatomic ions, the oxidation number is equal to the charge in the ion. So think back to the nomenclature. Remember, it said ionic compounds. Ionic compounds are a metal, typically, which is a cation, plus a non-metal, which is an anion. Or it could be a polyatomic ion. We'll talk about that in a second. Specifically in the metals, whatever the charge is on that metal, that's the oxidation state or number. Okay, so you know about the groups, group 1, group 2. Group 1 is going to be a +1, group 2s are +2. Remember, the halogen groups in ionic compounds are always -1. So you've got to keep this in mind when you're assigning these oxidation numbers. All right, rule number 3. And this is, of the rules I'm going to give you, really 2 of them are used most frequently. This is one of them. The oxidation number of oxygen in its compounds, okay, is usually -2, except, there's exceptions, in peroxide. So this is hydrogen peroxide. In that case, each oxygen will have a -1. All right. Now we're talking about not ionic compounds, but covalent compounds. So let's look at this. Here's water. Okay. Turns out the second rule I'm going to give you after this, or excuse me, the fourth rule is that hydrogen in its compounds is always +1. If that's true, each of those hydrogens is +1 and that oxygen is -2. Think about oxidation states in covalent compounds as who wins the tug of war with the electron cloud. Because of differences in electronegativity, both of those elements, atoms, are pulling on that electron cloud. Oxygen is a very electronegative element. It pulls the electron cloud towards itself, and so this is sort of imaginary. What would happen if we broke those bonds? Who would take the electrons and who would give them up? Well, the oxygen would grab one electron each from the hydrogen, and each of those hydrogens would let go of its electrons, and hence the oxygen's -2, and each of those hydrogens is +1. All right. Now, what about peroxides? Well, let me show you the structure of hydrogen peroxide. It's an oxygen bound to another oxygen and then something else stuck onto it. In this case, since each oxygen atom has the same electronegativity, neither of them wins the tug of war. So when we break these bonds, okay, each of those oxygens has grabbed an electron from the hydrogen. Okay. Now the hydrogens, we have 2 hydrogens at +1 and we have 2 oxygens at -1. So that's the exception. Oxygen in its compounds is usually -2, in peroxides is -1. Okay. Here's the second most commonly used rule. We said oxygen, hydrogen. Hydrogen in its compounds, with some exceptions, is pretty much always +1. Meaning that hydrogen always loses the battle, typically, of the tug of war, and says, here, take my electrons. Okay. Turns out that hydrogen can also act like a nonmetal. Remember, we've shown you that on the periodic table, hydrogen, you'll see it on the left side and the right side. Here's how it can behave like a nonmetal. In metal hydrides, what are metal hydrides? Well, a metal plus hydrogen. Metal plus hydrogen. The hydrogen will act as a nonmetal and grab that electron. Okay, so in other words, it does win the tug of war with its metal partner. So when we pair up sodium and hydrogen, the sodium, being a group 1 element, has a +1 oxidation number, and the hydrogen has a -1. All right, so there's your exception for hydrogen. Metal hydrides, I shouldn't say are not rare. They're out there. For the most part, anytime you're looking at hydrogen, it's going to actually lose a battle. It's going to be a +1. So rules 3 and 4 are the most common ones you'll use. Okay, number 5, fluorine, always -1. Why is that? Fluorine is the most electronegative element. So it will win the tug of war with any other element. It'll grab that electron, and hence it becomes a negative. All right. Here's another exception for oxygen. Sorry to throw a second one at you, but fluorine and oxygen are both very electronegative, but fluorine is more electronegative. So it will win the tug of war. And notice oxygen paired up with fluorine, the oxygen becomes positive. How is that possible? Well, because of this unequal electronegativity. You rarely see fluorine and oxygen together, so I wouldn't worry too much about that. Okay. Then finally, the sum of the oxidation numbers of all the atoms in a molecule or ion equal the charge on the molecule or ion. Don't worry, I'm going to go through some examples, but of course practice this. All right. So here are some examples. Determine the oxidation number for each element in each of these substances. Now, I need to clarify the distinction between the oxidation number and the per atom, or the atom element contribution. Let me do, we'll do this one, start off with. All right. That's the manganate ion, MnO4. So you look at that and you say, again, first things, look for oxygen, look for hydrogen. Well, there's oxygen, and we got 4 of them. So let me write this up here, MnO4. You notice it's got a net charge of -1. All right. Each of those oxygens is -2 by our rule. It's not a peroxide, it's not paired with fluorine, so it's -2. But there's 4 of them. So the total contribution then is -8. That's what I mean by this distinction between the per atom oxidation number and the total contribution for that element. So again, this is -8. So what is manganese in this case then? Well, to generate a -1, we need a +7. So the oxidation number for that manganese in this case is +7. Now remember, transition elements can exist in multiple oxidation states. In fact, manganese is a metal that exists in a whole bunch of different oxidation states. So I want to use that example first to make this distinction between the per atom oxidation number or state and the total contribution for an element. Okay, okay, so we got that one. Let's do, well, here's an exception, hydrogen peroxide. We already talked about that. Each of those hydrogens is +1, and because of that exception, each of those oxygens is -1. What about free oxygen? That's our rule 1. Free element, 0. So oxygen has a 0. Water, we've already gone through that, but let's do that again. Water looks like this. The 2 most common rules, look for oxygen, look for hydrogen. That oxygen is a -2 oxidation state, and each of these hydrogens is a +1. Simple enough. Okay. Iron bromide, let's focus on that. Ionic compound, right? So we're going to have, it's going to be some form of plus and minus here. Well, this is where you have to remember that group designation for charges. Bromides, halogen, so that's going to be a -1. Okay. However, there are 2 of them. Let me rewrite this. So each of those bromides is -1, which gives us -2. That's the total contribution for that element. So that makes the iron +2. Iron actually exists most commonly in a +2 or +3 oxidation state. So in other words, if that iron was a +3, we'd have FeBr3. All right. All right, so which ones have we not done here? Oh, let's do an exception. Calcium hydride, that's what I was talking about. There's that exception for hydrogen. Well, calcium is a group 2 metal, right? And what does that mean? That means it's going to be a +2, so that's its oxidation state, its number, and each of those hydrogens is -1. Since we've got 2 of them, the total contribution is -2. All right, let's do another molecular compound, right? Nitrogen and oxygen, remember 2 nonmetals. Well, we look at that and I say, rule number 1 that's most common, oxygen. I'm going to write this over here. So each of those oxygens is -2. We've got 4 of them, so we've got a total contribution of -8. So what do we need from the nitrogen contribution to give us a net charge of 0? Well, we need a +8. But there's 2 nitrogen atoms, so each of them is a +4. So again, in this compound, this dinitrogen tetroxide, each of the nitrogens is a +4 oxidation state, and each of the oxygens is -2. Okay. And I think that's it. We'll do carbonate real quickly. Carbonate, same thing, look for oxygens. Well, I've got 3 oxygens, so each of those is -2, and we got a contribution of 3, so that's -6. Now it needs a net charge of -2, so that must mean the carbon is a +4 oxidation number. So carbon's plus 4. Each of the oxygen atoms is minus 2. Now, let's apply that for looking at a whole reaction. That previous set of examples, that's what you need to do very quickly, because now you'll have to look at a whole chemical reaction, decide what's being oxidized, what's being reduced, okay, and deciding, is it an oxidation-reduction reaction anyway? Okay, sometimes you can have reactions that are not, and I'll go through one of those. So here's an example. This is a reaction of manganese metal plus oxygen. Right away, you ought to suspect this is redox, by the way. I forgot to mention this. Redox. This is the abbreviation used for oxidation reduction. Don't ask me why it got switched, but when you hear redox, that simply means an oxidation reduction reaction. Okay. Anytime you've got free elements combining and give you something else, you know there's an oxidation reduction because the free elements have an oxidation number of 0. So on this side, we've got the plus 2 and minus 2, right? Group 2 metal, magnesium, it's going to be plus 2. Oxygen in an ionic compound, minus 2. So that's clearly an oxidation reduction. Oxygen has been reduced. It's grabbed the electrons. Magnesium said, here, take 2 electrons. All right. How about this one? Calcium, this is what? This is a decomposition reaction. Remember, we had A going to B plus C. Decomposition reaction. Okay. Well, let's look at this. And this is where you got to be quick. So we're going to determine the oxidation number for each of the elements in each of the compounds. So let's start with this one. Calcium, group 2 metal, that's going to be a plus 2. Right? Because this is an ionic compound. Remember, this is a metal and this is a polyatomic anion. Okay. How about that carbon? Well, we're not done yet. Each of these oxygens, let me clean this up, plus 2. Each of these oxygens is minus 2. So we've got a total contribution of, excuse me, erase that, of minus 6. All right. So to get a neutral compound, the carbon then must be a plus 4. Calcium's plus 2, carbon's plus 4. You add those with a minus 6, and you got a neutral compound. So let me rewrite that. The carbon, because this is what I'll focus on, plus 4 oxidation state. How about on the right side? Well, calcium oxide, calcium is going to be a plus 2, oxide, is a minus 2. What about the CO2? Well, CO2, each of those oxygens is minus 2. We've got a contribution of 2, so this is, minus 4. All right. So what is that carbon then? Carbon is plus 4. So what's happened here? Well, pretty much nothing. This is not an oxidation-reduction reaction. All right. This is the only way you can tell this is by assigning the numbers to each of the atoms, each element atom in each compound. So no redox. All right, one more. Again, before I move forward, the biggest clue you're going to look at is look for free elements. Well, here you got oxygen. This is the combustion. Remember, that's another reaction that we had, combustion. The reaction of oxygen with a hydrocarbon, in this case methane. Okay, free element on the left side of the equation. It's now in a compound on the right side, reduction, oxidation reduction, If you wanted to assign numbers, let me just show you something, what happens to the carbon here. The carbon in methane is minus 4, oxidation state, right? Because each of these hydrogens is plus 1. We have 4 of them, so that's, plus 4. So the carbon's minus 4 with the plus 4 gives us 0. What about the carbon in the CO2? Well, we just did it up there. Each of these oxygens is minus 2. The oxygen's minus 4. That must mean that the carbon is plus 4. So notice what's happened to carbon. It's gone from a minus 4 to a plus 4. In theory, it's lost 8 electrons. Right? So that's clearly oxidation. Again, on the number line, okay, we went from minus 4 to plus 4. That is an oxidation. What's been reduced? Well, the oxygen. Oxygen went from 0 to its characteristic minus 2, minus 2. All right, let's do a couple more. Silver nitrate plus hydrochloric acid gives us silver chloride plus nitric acid. All right. Ionic compounds. We've got an ionic compound here. So silver's +1, as you learned in the nomenclature, always +1. What about that nitrate? The nitrate, let's break it out here. Polyatomic ions got a net -1 charge. All right. So each of these oxygens -2, contributions -6, therefore the nitrogen must be +5. All right, all right. How about the HCl? Hydrogen in its compounds, +1, chloride, halogen group, -1. Well, let's see if anything's been oxidized or reduced. Silver chloride, another ionic compound. Charges, oxidation numbers haven't changed. Silver's +1, chloride's -1, so no change there. Nitric acid, again, no change. That nitrogen is still going to be +5, +1, and each of these +2. So this is no redox. And then one final one. I'm not going to assign numbers, again, because your tip-off here should be free element, copper, which is 0. Now you see it in a compound on the right side in copper nitrate. What would that be? What would the oxidation state for that copper be? Well, again, using your memorization of the polyatomic ions and charges, you know that the nitrate is a -1, but we have 2 of them, so that must mean copper here is +2. Copper typically exists as a +1 or +2 oxidation state. In this case, it's a +2. Okay. We're going to continue with this oxidation reduction in a subsequent video. I want to break it down to give you a little rest here. We need to talk about some characteristic reactions of metals and how they play into this oxidation reduction. So that's coming up.